This lecture will be a brief overview of conic sections. Conic sections are called that because if you take two cones that are point to point, as these two are, and you pass planes through them, you can get the different conic sections. And so to get a hyperbola, we can pass a plane through at an angle different from the angle of the cones. And as you can see, the intersection of the plane with the two cones would be a hyperbola. A circle is specifically a plane which is exactly perpendicular to the axis going through the cones. The top view looks a little elliptical. That's just because of the aspect ratio of the way it's graphed here. That would be a circle, and you can compare that to an ellipse, which is the same sort of thing, but you see now it's going in an angle. Now, with the ellipse, we're still only hitting a single plane like the circle, or a single cone, not both cones, and now it's clear as I look at it in this way that it's much more eccentric. It's clearly elliptical. A parabola is when you go exactly parallel to that angle of the cones, and so you hit one cone and you get the parabolic shape. And then we have a couple types of degenerate conics. This is one, just the single one going through the single point here. So that would be something like x squared plus y squared equals 0, where you have one single point. This would be something like x squared minus y squared equals 0, where you have two intersecting lines. So those are the degenerate conics, but of course normally we deal with the hyperbola, circle, ellipse, parabola. So now taking a look at some equations, and then we'll go on to some of the interesting properties. And the way we can derive these is by using locus definitions. For a circle, all the points in a given distance from a center. An ellipse, all the points, the sum of the distances from the focus, the two foci are the same. Hyperbola, the difference between the two foci, that difference is the same. Hyperbola, the distance between a point and a line, that is the directrix, is the same. And so you can see the way that we trace these things out. So now looking more specifically at some of the conics, here's the circle. This is getting the locus by drawing it out. Here we have the entire thing. As far as deriving the general equation, we use the distance formula, and there it is as a graph. And so you can see the equation x minus h squared plus y minus k squared is equal to r squared, where h and k is the center and r is the radius. Here's a parabola. We'll skip the construction, just show the parabola. And then here's the general equation where, again, we use a distance formula. Start that over. Again, we use a distance formula, and the distance from the point to the line and the point to the focus is going to be the same. And then if we take a look at a specific equation, we'll use a horizontal directrix just for an example. And we can move this around, and while that's changing we're changing the different parabola as we go. Here's an equation. So the vertex is at h and k. Here the vertex is at 0, 0. I can move that along, and you can see how it changes the equation accordingly. So x minus h squared plus k. And then what I have out front is 1 over 4 times this distance from the vertex to the focus of the vertex to the directrix. An ellipse, we get the locus by sweeping this out. And so the distance, the sum of these two distances has to remain constant. And then let's take a look over here at the actual ellipse itself, major axis, minor axis. Here's now the equation, the specific equation we have here. It's centered at h and k, which is 0, 0 in this case. The semi-major axis is 5, goes down here. Semi-minor axis is 4, goes over here, and we have 1 over here. This is some relationships between A, B, and C, where C is the distance from the center to the foci. The general equation, again, you don't need to know this for this class, is derived once again from the distance formula, where these distances have to remain constant. So here's the proof in its entirety. And then looking at the hyperbola, getting the locus. Again, the differences have to remain the same between those two. And of course, hyperbolas are going to have asymptotes to them. So here's the hyperbola. And we take a look at the equation. We have our asymptotes here in yellow. Our distance A over here, distance B here. From there you get the box, and the diagonals give you your asymptotes. The specific equation is given here. Notice, usually we see the x squared over a squared minus y squared over b squared equals 1. Notice the minus is just written over here. It's really the x squared minus the y squared term. If the y squared is positive and the x squared is negative, then the hyperbola would have its wings on top and bottom as opposed to left and right. And once again, the center of the hyperbola, h and k given here, and we have a different relationship between a, b, and c. So here's a general form of things. Ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. And when we get into rotations, that's going to involve the b term. And so that changes all sorts of things once you start messing around with b. You can get different conic sections as a matter of fact. But there's in this form, it's hard to predict necessarily what these changes are going to do, changing these particular variables. And then, of course, we have this idea of eccentricity. If the eccentricity is 1, we have a parabola, exactly. If we go bigger than 1, we have hyperbola, so there's the other wing down there. Between 0 and 1, we have ourselves the ellipse, and then as we get down to 0, we have a circle. Of course, this one it's set up with a radius of 0, so you don't really see much of it. Okay, now some properties and applications. We see when you spin these things around, you get the paraboloid, like satellite dishes, ellipsoids in the way planets that rotate, hyperboloids as we see in this museum, and these nuclear reactors. This is concentric circles, and as we move them over each other, we get this sort of hyperbolic lines showing up, as well as elliptical lines towards the center, as we see down below. A little hard to perceive at times. The centers are the foci, and the mutual orthogonality implies a perpendicularity between the circles at certain points, that is. Now we start to see some ellipses in here and the hyperbola sort of white shading out there. Reflections and collections. Here's one ray, and if you move this point around, if you move the point around, notice that as long as you're shining from the focus, you'll always be shining out straight. And this is sending points out, but we can also collect them. So this is sending them out from the focus, and notice they always go out straight, which has important applications, and it works the same way coming in. So for the satellite dish, you have a parabolic shape because you want to get the highest signal. So as the waves come in from a satellite, they focus all at the single point. They all bounce off and come right back to the focus, and so you get the strongest signal. Conversely, if you do it the opposite way, and we look at, say, a headlight where we're shining a light source out. If we emit light here from a light source, notice the light source doesn't look like it's at the focus, and look at how the light rays bounce off. It's not going to be a very effective headlight because it's not going to shine in one direction, in the direction you're driving. But if we move the light source to the focus instead, now what happens when we, well, it's doing it dynamically. Now what happens is if we emit the light, let's start this thing over again. Now the light's all going to go out straight, so we get a more effective headlight clearly. Same things in flashlights you would see. Okay, back over to here, and then finally for our falling bodies, because we have constant acceleration on Earth, assuming things like air resistance, we get parabolic curves. So that's what's going on here. And in physics, you'd study kinematic equations, which are given by these types of equations.